All right, welcome back. We're at 4.2 day 1 through day 2 log functions. Okay, we're going to convert between log and exponential forms of equations, evaluate log expressions without a calculator, graph log equations, and solve word problems involving logs. Sounds like a lot. It kind of is, so let's get going. Okay, logarithmic versus exponential equations. Okay, now definition for b greater than 0 and b not equal to 1 and x greater than 0. Holy cow. Okay, y equals log base b of x is a logarithmic function, and b to the y equals x is an equivalent form of the exact same equation. So basically this definition allows you to turn one equation into the other depending on what's more user-friendly for whatever you're trying to do. Okay, also notice there are no restrictions on the value of y. However, we do need to restrict b and x based on whatever is going to happen there. Okay, now well, basically what that means is, let's do x first. X is greater than 0 basically means you can't have the log of a negative number. All right, and the rest of that, the b greater than 0 and b is not equal to 1, well, basically we can't have the base of the log be negative, so right here, that's bad. Okay, don't want a negative base for a log, that doesn't work. And we also don't want it equal to 1, and the other form of this is a little bit nicer, because if we have 1 as the b value, then b to some, or 1 to some power, of course, is going to be 1. It's kind of a non-issue there. So some restrictions there just to kind of prevent negative things badly happening, or things that just are kind of a nonsensical sort of thing to go. All right, that's not overly important. Let's go ahead and do the stuff that's more important. Here we go. Using the definition, we can translate between logarithmic and exponential equations because there are times when one is more useful than the other, kind of like I mentioned earlier. Okay, so if I've got log base 3 of 81 equals 4, I want that in exponential form. Okay, well, basically the routine here, let me zoom in so we can do this a little bit better, is the base of the log is going to be the base of the power, and that power is the thing on the other side. So it's kind of like that 3 is going to squeeze in next to that 4 there. If you've got a dog at home, sometimes he wants to squeeze into a spot, and you've seen that before, and basically that's what that 3 is going to do. It's going to pretend it's a puppy and squeeze into the spot it wants to get into, whether or not there's room for it or not. Okay, and then after you do that, it's basically just going to be equal to the 81 on the other side, in this case at least, with the 81. All right, so that's kind of what happens in my mind where the arrows are going there, and what that really translates into is that little puppy squeezes in to the 4. Now that 4 then becomes an exponent, and that's equal to the number inside the log. Not a mathematical term, but makes sense to me. So log base 3 of 81 equals 4 is the exact same thing as saying 3 to the 4th equals 81. Again, it's just depending on the situation, one of those might be more useful than the other. Okay, especially if there's variables involved, which I promise there will be in the future here. Okay, let's get things zoomed back into a normal spot. All right, then if we want to convert 9 to the k equals 27 into logarithmic form. Okay, well, this is a little bit more difficult for two reasons. One, we have a variable. Now, our first example here, you could have rearranged those numbers into some way and said, okay, does that make sense or not? And if it didn't, you could try rearranging it a different way until you found something that made sense. Okay, the 9 to the k equals 27. Now, technically we could solve for k, but we're not going to do that right now. But here we go. Okay, looking back at the definition, okay, zooming in just slightly here for our definition. Okay, now notice the subscript there, let's use pink. The subscript of the log becomes the base of the power and vice versa. So in our example here, since the 9 is the base of the power, I know that's going to become the base of the log. So the first thing I can do, and okay, here I'm using paper like you used when you were first learning to write with your capitals and lowercase and all that kind of stuff to help separate where things are. Okay, but anyway, we've got log. Okay, and again, that 9 is going to become the subscript of the log, or the base of the log, so then that 9 should be kind of like below the kind of normal line in a proper subscript notation-y sort of way. Okay, and then if we look back at our equations again, okay, we can see, here we go. Okay, we can see that the number inside the log in the original form is the number that kind of ends up by itself. Okay, so in this case, that ends up being the 27 for us. So the number inside the log, okay, not the base, but the number inside the log, the 27, ends up going inside the log, kind of like I said. All right, and then from there we've got equals, and kind of process elimination, we've got the only thing left that we haven't used yet is the k, but I would like to point out really briefly that, again, back to our kind of definition here. Whoops, that was a little more too much zooming. Okay, we can see that the exponent here is the y, and if the exponent's the y, looking back at the other version, that's the thing that ends up kind of by itself on the other side of the log. All right, so notice that log is actually an exponent. Whenever we write log, we really mean an exponent of some sort. Okay, but zooming back out to get our final answer here, the exponent in this case is the k, so there you go. So 9 to the k equals 27 turns into log base 9 of 27 equals k. Now I confess that that's awkward, and my brain doesn't like it so much, and I'm guessing yours may not either, so my brain does like the converting the log into the exponential equation. So just like in the other one, we kind of pretend that puppy is the 3 that squeezes up against the 4 and then equals the 81. You could do that to check your answer here. Pretend that 9, so is a little bit of a check. Okay, take that 9, squeeze it up against that k, and we get 9 to the k equals, the number on the other side is 27. So happy face, that is what we started with. So the final answer is the thing on the lines right there, but the little check right there, definitely I think worth your time doing, especially if you're not very familiar with this. But anyway, there we go. Okay, now as we're doing this, you have to be very aware of implied bases. Okay, because anytime we say log and don't put a base in there, like a lot of times in mathematics, we imply something is usually a 1 in most cases. This is an implied 10. So when I say log d equals 3, that really means log base 10. Okay, it's otherwise known as the common log. Not really a major sort of deal, but that's the word that's used sometimes. All right, but anyway, now we can take that 10, pretend it's a puppy, squeeze it up against the 3, and get 10 to the third equals d. As one version of that, of course, you could say d equals 10 to the third if you prefer. But anyway, there's your exponential form. Again, there was no 10 in the original problem, but there was an implied 10 that does come into play. Okay, second example here, I've got natural log 14 equals 4x. Okay, now again, that is an ln, standing for log naturel. It's, I believe, something come up with by a French mathematician. That's why the linguistics are a little bit different there, where the adjective comes on the other side of the noun as opposed to what we're used to. We say natural log. The French will say log naturel. So that's why the L comes first and the N comes second there. Anyway, more to the point for what we're trying to do here. Okay, the subscript for natural log is kind of an implied e. All right, so doing the conversion here, the e is our little puppy that squeezes over to the other side, to the 4x. So hi, let me cuddle. E to the 4x equals, and then of course it's equal to the number inside the log, which in this case is a 14. So there's that guy. All right, so just watch out for those implied bases. They definitely come into play, and they are not an implied 1, excuse me, 1 like we normally have in mathematics, but anyway, implied 10 and an e, based on whichever you see, log or just ln. All right, moving on. Okay, evaluating logs without a calculator. Now this is what some people find fairly challenging, but anyway, here we go. Keep in mind that a log is effectively asking what exponent is needed to make the base equal to the number, quote unquote, inside the log. So the expression log base 5 of 125 is basically asking what power of 5 equals 125. That's all it's doing. Okay, now consequently, the expression log base 5 of 125 is equal to 3, and of course, in case that's not obvious, it's because 5 to the third equals 125. So again, you're asking what exponent takes the subscript to being the kind of normal font number. All right, so that's the deal. So looking at our examples down there, okay, first one is log base 4 of 16. Now this is the gimme. Okay, hopefully you can kind of ask yourself, hey, 4 to what power, so that's supposed to be a question mark in case it's hard to tell, is going to be 16, and yeah, in that case, I expect you very quickly to look at that and say, oh, okay, well, that's 2. Okay, so boom, there it is. Now, you could use an X instead of a question mark, but what I want to impress upon you here is there's no X in the original problem, so if you do that and then tell me X equals 2, you're kind of not doing what I'm asking you to do. I'm not asking you to solve for X, I'm just asking you what that thing's equal to. If you want to use the X instead of the question mark to kind of help yourself, that's fine, but your answer should not include X when you're giving it to me, unless there's an X originally in the problem someplace. All right, moving on, let's switch colors because it's fun. Okay, now I've got log base 7 of 1/7. Okay, so again, same thing. 7 to what power is equal to 1/7? Okay, now notice the fraction showing up. Now, when we're using exponents, the way to get a fraction when you don't have one to start with is to use a negative exponent. All right, so the fraction pretty much tells me there was a negative exponent at play, so really I'm just asking myself, hey, what power of 7 gets me to 7? And that's the first power, and then I just have to stick a negative onto it. So what that tells me is that whole thing is equal to -1, because 7 to the negative first would give me 1/7. Okay, moving on. All right, our third guy over here, I got log base 81 equals 9. Now you might go, oh, 2. Well, wait a minute, hold your horses, because that means that 81 squared equals 9, and I'm pretty sure that's not right. We want to take 81 to some power and get 9. All right, now here's where this thing gets a little bit tricky. Okay, but notice the number got smaller but didn't become a fraction like the previous example, it just became a smaller whole number. All right, so basically what that tells me is we had to do some kind of a root. All right, now remember exponents and roots are interchangeable depending on if you're using a fractional exponent versus the appropriate type of root. All right, so just to really beat this home, square root of 81 equals 9. Well, square root of 81 is also written as 81 to the 1/2 power. So basically what I've done there is shown, hey, wait a minute, 81 to some kind of a power can be 9 as long as that power is a fraction, specifically in this case the fraction 1/2. So the final answer is 1/2, just that other stuff was kind of a thought process to get you there. All right, yes, I know it's a little bit tricky, but you can do it. All right, let's go to the next 3 examples. They get a little bit trickier from here, although this first one is actually so easy it's hard. All right, so anyway, using what we've already used, let's stick with the pink since it's not on the screen right now. Zoom in just a hair. Okay, now again, log base 3 of 3 to the 6th. So again, I'm asking myself 3 to what power is going to be then 3 to the 6th power? Well, that's kind of a silly thing right there because, hey, if I have to take 3 to some power and I'm going to get 3 to the 6th, well, that thing, the question mark, sure better be a 6 because it's hard to get 3 to the 6th by using any other thing other than the 6th power of 3. So if that made sense, I hope so. Yeah, it's just something as simple as that. Okay, now the next one over here, okay, got natural log of the square root of e. All right, well, we've done something like this already, but I don't want to give it away, but here we go. Okay, now again, remember there's a implied e kind of tucked in there as a subscript, not as anything with the root necessarily, but there's really an e there. So again, what we're asking is e to what power, and it's the e from the subscript, equals the square root of e. Okay, now again, as I did earlier, that square root of e could be rewritten as some kind of a fractional power if we wanted it to. So we kind of have e to the something equals e to the 1/2, and at this point it's kind of a, hopefully fairly obvious thing because the bases are the same. Well, if some base to a power is equal to some base to some power, those two powers better be equal. All right, so in this case, that question mark sure needs to be a 1/2 to be equal to e to the 1/2 on the other side. All right, moving on, and again, let's zoom in a little bit. I'm going to lose a hair of my work there, but here we go. Last one, log of 1. All right, now again, there's an implied 10 kind of tucked in there. And again, what we're asking there is 10 to what power is equal to 1. Okay, now this might seem a little crazy because you're like, well, I can't really do a root. It doesn't work. And if I use a negative exponent, I'll get some kind of a thing with 10 on the denominator, and that doesn't work. But hopefully what you remember is if I take the 0 power of anything, I get an answer of 1. So in this case, the base was actually irrelevant, but I need something, some kind of an exponent that gets me to 1 using whatever base I happen to have. And the convenient thing there is the 0 power will turn any base into 1 other than 0, but let's not get into that discussion right now. All right, that's a discussion for another time for sure. Okay, but anyway, there's a thought process that'll get you pretty much through any situation I might give you. But of course, ask me in class to clarify any of that if you didn't quite follow. All right, let's get to graphing. All right, so graphing a function like y equals log base 6 of x is not something our brains like very much, but if we rewrite the equation into that exponential form, then things might go a little more smoothly. Okay, so y equals log base 6 of x we've got right there. Okay, again, I'm going to zoom in just a hair for now so we can see things a little easier. All right, well, again, exponential form, and if the equation in this form kind of messes with you, I recommend getting rid of the y equals on the left side, putting it on the right side, and then maybe your brain likes it a little better. Okay, but moral of the story, we get 6 to the y equals x, doing that little puppy snuggling in conversion sort of thing. All right, and once we got there, notice that, as I can zoom back out and see it, okay, notice that it's easier to pick nice y values and find x values from there. Because, yeah, I can pick various numbers for x, but then I've got to figure out 6 to what power gets me that number. Ooh, that's a little bit challenging. But if I just pick powers of 6, meaning picking y values, that should go a little more nicely. So I can just take my y values in this case, pick 2, 1, 0, negative 1, negative 2, and then I can take various powers of 6s, specifically 2 down to negative 2, and then I'm just simply calculating something like that instead of trying to solve some situation. So it's a lot easier to pick y's and figure out x's in a log scenario. All right, but anyway, let's kind of run through that. 6 squared, of course, is going to give me a 36. Okay, 6 to the first gets me 6, 6 to the 0 is 1, 6 to the negative 1 is 1/6, and then 6 to the negative 2 gets me 1 over 36. All right, so maybe we can see what's happening here. We got a few points we can plot. Okay, now the x is 36. That is going to be a little bit challenging to fit on the screen, but I'll do my best. Here we go. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, and then one little extension gets me 36. Okay, we're going to call that pretty good. All right, now in the y direction, notice I don't have much going on, so I can go 1, 2, 1, 2, and not really have too much to worry about there. But again, that's 5, 10, 15, 20, 25, 30, and 35 to get the job done, and then just simply 1, 2, negative 1, negative 2, there. All right, so a little bit crowded x-axis, but we can manage. All right, now we just plot our points. Well, let's see, 36, 2 gets me way the heck to the right, and then up to 2. And then we've got 6, 1, so we don't have to go very far over for that. I've got 1, 0, so that lands me pretty darn close to the y-axis there. And then I've got 1, 6, negative 1, and then 1, 36th, negative 2. Holy cow. Okay, we're going to have to squeeze those in, but if I go to the right 1, 6, then down 1, I'm here. And again, let's zoom in a little bit, but now I need to go 1/36 over and then down. So notice the 1/36 to be slightly closer. Okay, we'll take a wild guess what's happening as we get closer and closer to 0 in the x direction. Okay, yeah, that's going to be an asymptote right there. If you want me to give a much longer description of that in class, I'd be happy to, but I don't want to make the video too much longer. All right, and I do know this is a review of sorts, so hopefully you know that. Otherwise, again, please ask in class. Okay, so we do have that asymptote running down there, and that asymptote is going to be y equals 0. I'm sorry, that's not y equals 0, that's x equals 0. A little brain fart there, pardon me. All right, so the asymptote is x equals 0. Okay, now in terms of the rest of the stuff that's on the screen that I've not yet mentioned, domain and range, okay, we can kind of see what's going on. Okay, now the domain, okay, notice that we're to the right of that asymptote and there's nothing to the left. So basically that tells me my domain now is going to be x is greater than 0. So again, it starts at the asymptote and goes to the right, very much like the exponentials we had, kind of started at an asymptote and went either up or down, although specifically up based on the ones that were in the last video. All right, now the range, here's where it's maybe not obvious, but hopefully it is. We can see on the kind of the left side of our curve, that guy is going straight down, and it's going to go all the way down to infinity, negative infinity actually, so boom, there it is. All right, now on the right-hand side, it's going up. But the question is it leveling off, or does it keep going up forever? Well, the answer is it does keep going up forever. Because again, we're free to pick any y values we want here. All right, so I can pick 6 to whatever power. There's no real limit to the power I can put on there other than my own imagination of the size of numbers I'm eventually going to get. So anyway, moral of the story is our range, this thing, even though it looks like it's leveling off on the right side, is rising just really, really slowly, and it does go up to infinity eventually. So our range in this case is going to be all reals. All right, so that's the basics of a log graph. And again, you can certainly graph that thing by hand, as I just did. No calculator necessary. All right, there you go. All right, so let's take another one with some shifts. So take care of any shifts by making your your initial XY chart based on the unshifted version of the equation, and then apply the appropriate shifts by adding extra columns. Okay, so I've still got my 2 down to negative 1, 2 down to negative 2. Okay, now again, my initial y value here is going to be based off of, again, ignore the shifts. The +1, remember, is going to be a shift left 1 unit, and the -2 is a shift down 2. So I'm really just working with y equals log base 3 of x for now, and again, that's better written as 3 to the y equals x. At least that's how my brain tolerates it a lot better. Okay, but since we do have the shifts, we're going to add extra columns on here to accommodate those shifts. All right, so anyway, here we go. I'm going to take 3 to the various powers I have in my y column, and 3 squared, of course, is 9. 3 to the first is 3, 3 to the 0 is 1, 3 to the negative 1 is 1/3, and then 3 to the negative second is 1/9. All right, so there we go. Now we do need to mess around with those shifts. All right, so anyway, we've got left 1. So here we go. Left 1 means I'm subtracting 1 from everything in the x direction. And yeah, we're going to be subtracting 1 off some fractions. So again, maybe those mixed numbers come in handy or something of the sort. We'll see what happens when we get there. But subtracting 1 off of 9 is easy. That's 8. 3 minus 1 is 2. 1 minus 1 is 0. And then the 1/3 minus 1, well, that's negative 2/3. And then the 1/9 minus 1 is a negative 8/9. Okay, again, make sure you ask me if you're not sure what I just did. All right, now in the other direction, we're going to go down 2. All right, so, well, down 2 in the y direction. Alrighty. Okay, again, I like my chart all the way filled in. And all kinds of nice brackets and lines and everything holding everything together. But anyway, here we go. Well, 2 minus 2 is 0. 1 minus 2 is negative 1. Negative 2, negative 3, and negative 4, filling things out. Okay, and then again, remember the middle stuff is kind of was temporary, now it's gone, and kind of the outside edges are the x and y coordinates that we're going to stick with. Okay, so looking at what I have here in the x direction, I go as high as 8, so that's not nearly as bad as last time. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10, there's 5, and I think I can get away with that. Okay, now since we did a downward shift, okay, we only need the y values of 0 down to -4. So if you want to put some in the x direction, that's fine, but we need 0, 1, 2, 3, 4 in the y direction. So there's -4, -3, -2, -1. Okay, again, for symmetry, because I don't know, it's honestly bothering me not to have those on the other side. 1, 2, 3, 4, and 5. Oh my gosh, I totally blew it. There we go. Okay, wow. All right, you don't want to have my brain. It does weird things to you. All right, but anyway, here we go. Just plot our points. I've got 8, 0 as one of my points, so 8, 0 puts me right there on the x-axis. I've got 2, -1, so over 2, down 1. Boom, there we are. Then I've got 0, -2. Okay, and then I've got some negatives right there. It looks like I better go in the negative direction a little bit here with my x-axis, so I'll get a couple tick marks that way. Put a -1 next to that, -2 there. Alrighty. Okay, so that -2/3 means I got to go a little bit over to about close to -1, although again, pointing some stuff out here. Okay, notice we've got the left 1 shift. Okay, so the asymptote normally on the y-axis gets shifted left 1, so probably a good thing to do, in my opinion, is to draw that asymptote where it's been shifted to at -1 first before you start plotting those little fractiony points, because they do get a little bit messy. All right, so if I go over 2/3 and then down 3, okay, I get something about right there, kind of hits a 3. Now notice -8/9 is more negative than the -2/3 was. So I go a little bit further, but again, I can't go very far because there's that asymptote holding me down. And I go down to -4 in this case, so I get a point about right there. And again, I get this nice logarithmic curve looking thing, which again goes all the way down to -infinity, and it does work its way slowly up to +infinity. It just sure takes an awful long time to get there. All right, so there's a shifted log graph for an example. All right, moving on to some word problems. Okay, now several things in the real world follow logarithmic patterns, such as the Richter scale that measures earthquake intensity and decibels that are a unit of sound intensity. Okay, so here's a word problem based on sound. Okay, the loudness level D of a sound measured in decibels is given by the formula D equals 10 log of 10 to the 12th times, that's an I in there, in case it's not clear, where that I is the intensity of the sound in watts per square meter. All right, now a typical lawnmower creates a sound intensity of 2.6 times 10 to the -3rd watts per square meter, so notice that's an I. Okay, now we're not talking about the imaginary unit, we're talking about the capital letter I that's in this problem, so don't confuse those. So how many decimals does a typical lawnmower make, rounded to the nearest tenth of a decibel? Okay, now don't get freaked out because it's a word problem, because really we're giving you the formula and then telling you what number to plug into it. All right, so this one should hopefully go pretty smoothly. We've got D equals, okay, the formula has a 10, and then if you like the time sign there, go ahead and put it in. And then log, and again, it is log base 10, and again, most calculators work on log base 10 by default. If you have an Inspire, you might have to type in the subscript for your log. It just depends on the model calculator you have. Okay, but anyway, we've got that parenthesis there. Now we got 10 and then times the I, and we were told in the problem the I is 2.6 times 10 to the -3rd. All right, so depending on how you are with your calculator, you should be able to type that thing all at once. If you're not sure how to do that, do definitely ask. Again, the 2.6 times 10 to the -3rd, a lot of calculators will have scientific notation capabilities, and you can type that in as 2.6, and then there's usually a button that has 2 capital E's on it. You might have to hit Shift to get to it, depending on your calculator, or it might be one of the normal buttons. And then on the display, it just gives a single capital E, and then you just type in the -3rd. Okay, that means 2.6 times 10 to the -3rd if your calculator accommodates scientific notation that way. So again, you have to determine what it is in your calculator. Again, if you don't know, ask me, and I will help you through it in class. All right, but anyway, punching all those buttons in your calculator, if you can pull that off appropriately, should get you 94.1497 and a whole bunch of other decimals. However, that's more decimals than I needed because we just said rounded to the nearest tenth, and so rounding that to the nearest tenth is 94.1, and then dB like that is the abbreviation for decibels. There you go. If you don't like that abbreviation, just write the word decibels out and you'll be just fine. All right, one more word problem and we'll be done here. Okay, students in class took a final exam and then as part of an experiment took a similar exam over similar content every month for the next 12 months. So there we go. Okay, the average score on the exam followed the model below, where P is the average percentage and X is the number of months since the class ended. All right, so again, we've got our formula there, 72 minus 12 times the natural log of X plus 1. And what's the average percentage for the tests for students taking part in the experiment 8 months after the class ended? Okay, now again, it does say that X is the number of months earlier, so basically here we go. P equals 72 minus 12 times, and again, if you want that time sign in there, go ahead and put it, natural log, and again, 8 is the number of months. In this case, it's 8 plus 1. Okay, now me personally, I would just simplify the 8 plus 1 to 9 before I typed it in my calculator, but go with whatever. Your calculator will handle 8 plus 1 just as easily as 9. But again, make sure you can type that in and get 45.633 and a whole bunch of other stuff. Now this one didn't include directions, so one possible answer, if I want to round to, let's say, the nearest tenths of a percent, it'd be 45.6%. If I just wanted to round to the nearest whole percentage, it'd just be 46%. Again, without directions, I would accept anything that was reasonable in terms of what answer you gave. But of course, if there are directions exactly how to round, then of course give that exact type of answer. All right, but anyway, there that is. That was technically all review, so hopefully that all made sense. But if not, of course, please ask in class, and I'll clarify anything that I can. And I'll see you there.